ion is basic, you can put acid into the water and it will help the solute to dissolve. Because the hydrogen ions from the acid will respond with the basic ions, of the little bit of basic ions, and they will drive the equilibrium to the right and cause the solute to dissolve. Well, another tactic or strategy that we have for making things dissolve that won't otherwise dissolve very well is to produce a complex ion. And that's what I'm up to today. So in chemistry, you've learned that when you have ions present in a solution, or any ions just anywhere in general, ions tend to attract positive to negative. They get together, and when they get together, the positives and negatives need to become neutral. That doesn't always happen, and that's what we're going to find with complex ions. The key to a complex ion is that thing right there. You have to have a transition metal ion present. The main group elements, like the group 1s and group 2 ions, they don't ever make complex ions. It's only the transition metals. Transition metals in the middle of the periodic table, I know we haven't covered this year, but they have d orbitals that they're filling. And when you have an ion in a transition metal, it probably has empty orbitals somewhere on it, even s or p orbitals, that what happens is, I'm going to go ahead and uncover something. You don't have to write this down or try to draw it. In fact, it's quite hard to read anyway. But we have in the middle of this thing a copper ion. Copper plus 2. Can you read that it's copper plus 2? It's kind of sketchy. But the copper plus 2 ion has empty orbitals in it. It's got orbitals that are not being used. Orbitals are little places where 2 electrons can be found. There's 4 ammonia molecules around the copper ion. And the 4 ammonia molecules each have a nitrogen that has a lone pair on it. Now the lone pair will find some of the empty orbitals on the copper ion, and the lone pair will actually occupy that orbital. Orbitals have room for 2 electrons, and since the copper doesn't offer any electrons to it, that lone pair will just stick itself onto the empty orbital on the copper. And so 4 of the nitrogens can do that. So the copper winds up, really the better representation of it is like this. You can actually read this. Those are actually covalent bonds now. A covalent bond is when you have an orbital that's occupied by 2 electrons, and those 2 electrons are shared by 2 atoms. And so that's the nitrogen on each ammonia molecule is making a covalent bond to the copper atom. They don't have a fancy name. They're just called, like this is called the copper ammonia complex. So the ammonia molecule is neutral. This is not the ammonium ion, it's the ammonia molecule. So there's a copper plus 2 ion with 4 neutral things that have bonded to it. So overall, the whole thing still has a positive 2 charge. This is a very stable ion. Those bonds, this thing is good. I mean, it's just good like that. Not only are they stable ions, they don't just break apart easily, they're very soluble. So copper, sometimes with, depending on what its anion is, when it's in a compound, a lot of copper compounds are not soluble. You just put it into water like copper oxide. It just won't dissolve, nothing. If you can take that non-dissolving copper compound and drop some ammonia into it, that will cause copper to disrupt its equilibrium, and it'll make complex ions with the ammonia, and then pretty soon all that non-dissolving stuff is all dissolved. because this formation of the complex ion will shift the copper dissolving equilibrium. So this only happens with transition metals. And these little molecules on the outside here that bond to the copper, they're called ligands. If you're in AP Bio, you may call that a chelating agent. Complex ions are known as chelates sometimes. I don't think there's anybody in here, though, that's in AP Bio, is there? Next year, maybe, some of you. Mitchell, you're not AP Bio, are you? You ever talk about chelates? Haven't you? Really? I thought you did. Okay. I didn't. I thought that in bio you called them chelates. All right. Here's an example of another complex ion, the silver ammonia complex. Now, the silver ammonia complex is only going to need 2 ammonia molecules, where the copper used 4. And it has to do with what the charge on the metal is. If you have a charge of +1 on the transition metal, it's only going to have 2 ligands attached to it. If you got a charge of +2, it'll have 4 ligands attached to it. So whatever the charge on the metal is, you double that number, that's how many ligands are going to go around it. Pretty simple. So the ligands wind up getting added one at a time. Now we're not going to do much with this, but I do want you to see that, like in this case, I chose this one because there's only 2 ammonias, so we'll have 2 formation constants. So this is what the chemistry looks like. The silver ion will grab 1 ammonia molecule. Again, the ligands go on one at a time, and each ligand that attaches is going to have its own equilibrium constant. So we've got the silver attaching to 1 ammonia to make just a silver in a single ammonia complex, and it has a certain K value. So you notice the K value means it heavily favors the production or the formation of the complex ion. And this doesn't last long, because as long as there's another ammonia molecule around, this ion will take another ammonia molecule and it'll make Ag and H3 take it twice. And you can add as many Ag or NH3s on, it will not change the charge on the silver because you're just adding a bunch of neutral things. But it only takes 2 because it's got a +1 charge. It doesn't have enough room. So what we'll always see is that the individual addition of the ligands will all add up to an overall formation constant like this. So these 2 add up together. This complex, that and that term cancel out, do the same thing. So you wind up with silver plus 2 ammonias yields Ag and H3 taken twice. And then the Ks, of course, get multiplied. So I have a picture of this one too. It's similar to what we had before, but instead of showing the 2 ammonia molecules, I just put the number 2 out here. This actually is not me doing. I picked this up off of a Google image search. But yeah, there's the ammonia molecule with that lone pair. That lone pair is a big deal because that's how the ammonia is going to attach to the silver. It makes a covalent bond. And there are 2 ammonias, so you got the silver in the middle with an ammonia molecule coming off of both sides. And if you're looking at this picture, you see that there's some terms up there that will be unfamiliar to you. Lewis acid and Lewis base. What is that? We've learned two definitions of acids and bases. We learned about the Arrhenius definition, which says that acids give off hydrogen, bases gives off hydroxide. Then we learned the Bronsted-Lowry, which had to modify the Arrhenius model. Bronsted-Lowry say that an acid is something that gives off hydrogen, and a base that is anything that takes hydrogen. In the 1900s, there was a guy named Gilbert Lewis who realized that acids and bases can even take on a bigger, more broad definition. So he proposed a new definition of acids and bases in which a base is something that has a lone pair that can be offered to something else, like a hydroxide. It has a lone pair. That's kind of the big player for bases. And then a Lewis acid is anything that can accept a lone pair of electrons. Whoops. We have had Lewis acids and bases cut out of the curriculum. We actually used to teach about Lewis acid and base chemistry back in the old days, but when they revised the curriculum for this class, they said Lewis acids and bases are out there. So I showed you this. Just really to tell you, if you ever have another chemistry class, you may learn another definition of acids and bases. Your professor will not be lying. It's true. It's Lewis. A little bit confusing too. It kind of has you turn your brain around where we're so used to hydrogens and hydroxides in acid-base chemistry. Then you see something like this. This doesn't look anything like an acid. It's a metal ion, but it fits the definition. Hydrogen ion can also fit a definition of an acid because it's an empty proton with no electrons around it, so it's got an empty orbital. So that's why hydrogen does fit the model of the Lewis acid. Okay, so enough about that. Anybody have any questions before I move on about this? So here's what I'd like to do. I've got the next two slides are going to have us comparing the solubility of silver iodide when it's in pure water at first. So this slide is not a complex ion slide. It's just something that we've already learned how to do. The next slide is going to take the same sulfur iodide. Instead of dissolving it into pure water, we'll try to dissolve it into something that has a ligand, and we'll see how the solubility changes. So I'm going to ask you to take a moment, see if you can do this problem. This is as easy as solubility problems get, so don't get it wrong.